We're now going to look at an example to motivate the convolution operator. And this example is from wireless communication, where we have a base station like this that wants to transmit a signal x of t, including some sort of message, to a cell phone over here. Now the base station transmits the signal like this, and because of the time it takes for the light to travel, the signal will be delayed. It will also be changed by some sort of constant factor, which may or may not be complex depending on how we describe our system. So the output signal, or the received signal at the cell phone, can be written like y of t equals c0 x of t minus tau 0, like this. Now the energy from the base station, the energy of the message x of t, won't just go in a single direction like this, but it will in fact spread out like this. And if we have nothing between the base station and the cell phone, the only part of the signal x of t which will get to the cell phone will be this component that we've drawn. Now, this is normally not the case. Normally, at least, the base station will stand on some sort of ground. So this signal will travel down to the ground, reflect here at this point, and then continue up to the cell phone. So we get another component, C1, x of t minus tau 1. Obviously, we can use, and we do use, different tricks to get the energy to go mostly in this direction. But there will still be some leakage in these other directions, and this leakage will normally need to be accounted for in some sort of sense. So what we get is we get the output signal by superposition is the sum of the components that reach the cell phone. Now I said that the energy will spread out in this different direction, and there are multiple places where these rays, we can call them, hit the ground, and reflect up to the cell phone. And maybe this one will hit a building over here, like this, and also reach the cell phone. This means that our output signal, y of t, can be written as a sum of different components with time delays t, tau of k, and constant dampening factors c of k. Now obviously it may occur that this component here, let's call that CA, x of t minus tau a, and this component right here, which will denote CB, x of tau b, it may occur that these two in fact have the same time delay, so tau a equals tau b. And we will call this tau today tau tilde for now. Now when this occurs, the part of the output signal that consists of these two components, CA, x of tau minus tau a, plus CB, x of tau minus tau b, this should be lowered anyway, can be written into a component CA plus CB times x of tau minus tau tilde. Now we can even go further and denote this one, C of tau tilde. And if we do that, we can write our output signal, y of t, as the sum of C of k k times delta tau, and this will be our different tau deltas, times x of t minus k times delta tau. And the way we do this is we just make this delta tau very, very small, so that k times delta tau will include all our different components that add up to our output signal. And we make k be any number from minus infinity to plus infinity. Now obviously there will be lots of times where there's no component for a time delay k times delta tau in this interval. But we just simply solve that by choosing c of k times delta tau to 0 in those cases. Now let's look at what we've got here. We can write a graph where we write our c factors as a function of k times delta tau. And what we typically will have lots of zeros in the beginning, and then at some point we'll have some sort of non-zero value. And then they might go around a little bit like this, and eventually they'll usually die out and go to 0 again. This is quite a typical scenario. And obviously the smallest time delay we can have is represented by this direct line, because any other which is a reflection somewhere will cause a smaller or a larger time delay. So this one here will be tau 0. Now I already said that the energy from the base station will spread in different directions. But obviously it won't just spread in discrete directions like I've drawn it in the picture, but it will spread in all sorts, continuously, in all directions. So we'll have a large number of rays like this. And what will happen then is that this delta tau will become smaller and smaller. And so all of these components will come closer and closer together, like this. And as delta tau goes to 0, which is obviously what happens when we go from discrete rays into continuous rays, this function c of k of delta tau will go towards c of tau and become a continuous function. And this c of tau is what you will note as your impulse response. Which often is written as h of tau, like this. Now let's think about what happens when delta tau goes to 0, while this function goes towards a continuous function. What happens with our output signal? Well, what we had a sum of these different components, but now this is a continuous function. So what happens is that this sum here becomes an integral from minus infinity to infinity. And our factors become a function, c of tau. Our signal with delays becomes a function x of t minus tau. And then, of course, we integrate over to tau. Now this, I think you should recognize as the convolution integral. So what you really get is that when you convolve something, you're really just taking the sum of the energy of all the different time delays that you have in your system. And in this case, with the wireless communication system, we can even represent that as multiple rays. But there will always be different time delays. And the convolution is just summing up all of this energy. So it's really, even though the convolution operator might seem strange when you look at it at first, it doesn't do anything else than sum up all the different components that add to our output.